Good evening.
Hi, everybody, and welcome to this evening's webinar, Understanding Hydraulic Fracturing. This is Barbara Gottlieb with Physicians for Social Responsibility. I'm delighted to welcome you to the second in our series of 3 webinars on hydraulic fracturing. Our presenter tonight, and I'm delighted to be able to introduce him, is Dr. Anthony Ingrassia, Dwight Seabaum Professor of Engineering at Cornell University, and representing physicians, scientists, and engineers for healthy energy. Dr. Ingrassia is a well-known expert on hydraulic fracturing, and in this presentation tonight, he'll be explaining to us what this fracturing process looks like, how it's part of a larger process of unconventional extraction of natural gas and also of oil, and how this process, especially in regard to natural gas extraction, is leading to high and alarming levels of leakage of methane, a serious climate change gas. We have on the technical panel my colleague Julia Morgan, also of Physicians for Social Responsibility. So Julia, if we can, let's turn the microphone over to Dr. Ingrassia, and I think we're ready to go. I don't think they can hear you.
Julie, am I live?
Yes, you're live.
Okay, thank you.
Go ahead.
Thank you very much, Barb, and thank you all for attending and participating with me tonight. It's, again, an honor to have the opportunity to address members of PSR. As you heard, the informal title for my interaction with you tonight is Understanding Hydraulic Fracturing, but as Barb just intimated, there's more to the issue than just hydraulic fracturing, and I think you're going to understand that in just the next few minutes. So really what I'm going to be talking about tonight is much more than fracking. It's really the science of extracting gas and oil from shale, the latest documented evidence on leaking wells, emissions, and some implications for national energy policy. So let's get started right away. If we had all the time in the world, I would like to talk to you for hours tonight about the 4 topics I'm showing you on slide 2 under the general title of Why Not Shale Gas and Oil. But we don't have time for everything, so I'm going to cover only the first 2 topics listed here. And the first one is necessary because I have to bring you all up to a common level of understanding of what it takes to get gas or oil out of a shale formation. This is all about shale. It's not just about fracking. As you'll see, fracking is a relatively small part of that entire process, which I will describe as being spatially intense, involving a very significant and very pervasive heavy industrial impact, both during and after the development of shale wells. And this leads to significant air, water, light, sound, and dust pollution and the attendant harms on human health. We'll then transition to the second topic listed here, which is that shale gas, contrary to what you hear on TV every night, and even from the President, is not a clean fossil fuel. It is not helping climate change, it's making it worse. So let's get started on the first topic, and this is going to be a very, very quick tour, starting underground and getting to the surface of what it takes using state-of-the-art modern technology, the best available, best practices on the part of the industry to wrest oil and gas out of shale formations. So the first thing I'd like to make sure everybody comes away tonight understanding is that shale is really a matter of scale. Nothing is small when it comes to developing oil or gas from shale formations. So very quickly I want to show you what the industry intent is. With the picture on slide 3. This started out as an artist's rendition from a company called Chesapeake of what it really means to go from the surface down below into the layer of shale and extract the oil or gas from it. So what they're showing here on the surface image is 4 areas called pads. I'm indicating them with the cursor now. In this artist rendition that looks like a nice bucolic setting with just a couple of small tanks. I'll show you in a few minutes that that's not all is involved. But each one of those pads has multiple wells. In this case, there are 6 wells originating from each of these 4 pads. So you're seeing 24 wells being drilled. And I've added the dimensions. The artist didn't bother to indicate that these pads are typically only a mile apart in one direction and about 2 miles apart in another direction. And yes, they do drill down 4,000 feet or more into this layer of shale. But the whole idea, the industry intent here, is to capture as much gas as possible over the entire shale layer, and that shale layer can underlie entire states. I'll show you some images in a few minutes of Pennsylvania and what the industry accomplishment to date is and what its intent is. But when I say spatially intense, what I mean is you need a hell of a lot of wells. As you can see here, once the wells get underground and they turn and they're drilled along the shale in what are called laterals, the wells are only about 500 feet apart underground. On the surface of each one of these pads, each of these 6 well heads is only about 10 feet apart. So what you see with this fuzzy white stuff is an artist's rendition of fracking. That's meant to indicate that something is happening down in the laterals to stimulate the shale to give up its oil or gas. So the intent of this picture is to show that geology controls the development of gas and oil from shale. It's not a matter of potluck. It's not a matter of drilling a well and hoping you strike it rich. The point is that there's gas and oil everywhere where there's black shale. And therefore, the industry will want to drill everywhere, hence spatially intense development. I'm going to switch to the next slide and give you an indication from a bird's eye view on a real area just south of me here in New York of what this sort of spatially intense development would look like at the scale of human activity. So here you can see roads, highways, buildings, towns, and I'm going to superimpose on this image a set of yellow rectangles. Each one of those yellow rectangles has a red square in the middle. Each one of those red squares would be a pad. What we just saw would have many wells, 6, 8, 10 wells. And each of those yellow rectangles would be the drainage area for each of those pads. So as you can see, if the industry had an unencumbered access to a countryside, a county, a town, a whole state, this is what it would look like. This is spatially intense development. Let me show you in the next 2 slides what is actually happening in 2 counties in northern Pennsylvania. So here's a map of Tioga County. The northern border of Tioga County is on the border between New York State and Pennsylvania. So above this line is heaven, below this line is hell. And this is a map showing all of the pads and drainage areas that are being developed by one company, in this case, Shell. So as you can see, Shell has acquired leasing rights to a very significant percentage of this entire county. And the county is being chopped up into these more or less rectangular areas. And each one of those rectangular areas here has a black dot indicating the location of the pad. And I want to emphasize here that this is only one company's holdings in one county. And this company has only drilled about 5% of its wells so far. In fact, in the entire state of Pennsylvania, only about 5% of all the shale gas wells that will be drilled and put into production have been put into production. So anything you're seeing or hearing about problems in Pennsylvania, this is the leading edge. We have no idea of what the future will be in terms of cumulative impact or total insult to the environment and human health. We go just to the west, to Bradford County, actually, I'm sorry, to the east in Bradford County, Pennsylvania. Again, New York State is to the north. And here you see the holdings of a number of companies. There's 10 different colors here. Each color corresponds to the holdings, lease holdings of one company. And again, you can see more or less rectangular areas, and those black squares, and this more or less in the center of each of those areas is a pad. And from each of those pads, there are many wells. Again, this is spatially intense development, and they're just getting started. So Let me now show you what actually happens in each one of these drilling areas and on each one of these pads. It's not that beautiful, bucolic artist rendition that I showed you a few slides back. I'm going to show you a series of photographs taken at different locations in northeastern and southwestern Pennsylvania to show you what a pad actually looks like at different stages of its development. So this first image shows a pad which has 5 wells. I'm pointing with my cursor to the location of the 5 wellheads. As you can see, this is not a 1-acre development. It's about a 20-acre development. And you can see remnants of the fracking process. Some of the equipment is still there, but these wells are actually now in production. And you can see remnants of waste pits. These are man-made ponds that originally held fresh water, and then they held fracking water, and then they held fracking wastewater. And each one of these pits is man-made. It's supposedly lined with plastic, but as such, they're man-made objects and they leak. Not only do they leak into surface waters, but they are open to the atmosphere, which means anything that's in that liquid, and believe me, that's no longer fresh water, can evaporate into the air. Those are methane, VOCs, all the way up to benzene. And that is still legal in every state in the union to have open waste pits. This is the granddaddy of them all. This is a 7-well pad down in southwestern Pennsylvania. You can see that about 100 acres have been cleared for these 7 wells. Again, very large waste pits, road building activity, pipeline building activity. This photograph shows a little bit more of what I call the surface infrastructure. Too many people get hung up on thinking of shale gas as a well. Well, there's the well, but there's also a lot of ancillary hardware and industrial activity associated with each well. So in the upper right of this photograph, you can see the pad, which has 7 wells. Here's a large impoundment pond with a dam. Here are the nearby homes, and in some states, it varies by state to state because there are no uniform federal regulations controlling any of this. In some states, activities that you see here, the wells, the wellheads, the impoundment ponds, the condensate tanks, can be as few as 150 feet from an inhabited dwelling. This next image shows even more of the ancillary infrastructure because it shows not only wells and well pads, but also a compressor station. This is a relatively small one, and a processing facility. A compressor station compresses the gas coming out of the wells into a much higher pressure so it can go into pipelines. A processing facility cracks the hydrocarbons that come out and separate them into methane, propane, butane, ethane, all the way up to, if necessary, petroleum. So depending upon where you are, in which state, you can have just the wells and just the compressor stations, or you can have the wells, compressor stations, the pipelines, and the processing units, and the waste pits. This is all associated with the high-intensity development of shale gas and shale oil. This last image shows you, again, what happens when regulations do not exist, or regulations are totally inadequate to protect human health. So as you can see, these homes are only a few hundred feet from this waste pit. And what you can't see in this waste pit is a number of fountains. That is, the waste liquid in this pit is being sprayed up into the atmosphere to help it evaporate. That decreases the company costs from then having to truck large volumes of this waste liquid to an injection well out in Ohio or West Virginia. But as that material evaporates, anybody living downwind is subject to any of the VOCs or any other materials that evaporate into the air, none of which are good for human health. This is a photograph taken at night of what's called a flare. So we're going to be talking about methane emissions in a little bit, but during the process of developing a shale gas well or a shale oil well, almost always in the first few weeks, there's the necessity to separate out the gas that's coming back from the fracking liquid that's coming back. And one of the choices for what to do with the gas that comes back at that point is to just burn it. on site in a flare. So you get an idea here that this is not a candle. This is a couple of 100 feet high flame. I'm going to show you a video in a minute of what this looks like and sounds like. At nighttime, you can't see the fact that that's not a nice, clean, blue flame that you get from your gas stove in your home. So I'm going to show you a video.
Look at that. That's air pollution. Boom. Unbelievable. Flames are higher than the trees.
You get the idea that flares aren't just pretty lights in the night. They're also very noisy, and they don't burn cleanly. If the gas is not flared, by the way, it's frequently vented directly into the atmosphere. And I will show you videos of what that looks like also in a few minutes. So getting back to some of this ancillary infrastructure, I mentioned compressor stations. Early on, 3 or 4 years ago in Pennsylvania, compressor stations were relatively small. Here's a photograph of a state-of-the-art superstation. Each one of those small buildings holds a 9,000 horsepower compressor running 24/7, 365 with attendant noise levels well above 110 dB and lots of gaseous emissions. Slide 9 shows you a now out-of-date map of all the compression stations along pipelines in the U.S. What this does not show is the new compression stations that are being developed in areas where shale gas is under rapid development, such as in Texas, Louisiana, Colorado, Arkansas, Pennsylvania, Ohio. So you're only seeing a small subset of all those compressor stations. There are now over 100 compressor stations in Pennsylvania alone built in the last 5 years. I'm going to show you another video now of what venting looks like from a compressor station. I hope you can hear it also.
We're going on for half an hour now. I called 911.
So I hope you're getting the idea that compressor stations and processing units are not clean. They are large sources of emission. In many cases, those emissions are not regulated. In many cases, they're not measured. And it takes amateur video to capture them. Getting back to the compressor stations, this is what they look like. These are 3 that were just built in the last 3 years in West Virginia and in southwestern Pennsylvania. These are literally large extraction plants. They're crackers. They're refineries. And they're being constructed very frequently, very close to human habitation. This is now, again, out-of-date map that shows all the natural gas processing plants in the country. What's not shown here are the recent ones that have been developed in Pennsylvania, Ohio, and West Virginia. But you get the idea that there are a large number of them, and that number is growing month by month. So in summary, I want you to take this away when it comes time to asking yourself, or somebody asks you, how does one get oil or gas out of a shale formation? And the answer is with one hell of a lot of industrial activity. That's spatially intense. It's invasive because it winds up absorbing communities. It absorbs residential areas. It is in almost every state in the union immune to zoning. And it requires a very large number, depending upon the region, tens of thousands to hundreds of thousands of wells arranged on multi-well pads that are clustered across the landscape. And connecting every one of those wells is a lot of significant ancillary infrastructure, and it's not just the wells, it's not just the fracking, it's everything else associated before the fracking and after the fracking with each well that I think is the largest risk to human health. So as I said, that was a very quick tour. I want to get to the second topic, which is current, obviously very current. It's difficult now to find a TV station that doesn't run a special show, a documentary, in addition to a major newspaper that doesn't talk about the latest paper that's been published on the issue of methane emissions from the development of shale gas and shale oil. So there are those who claim that the development of shale hydrocarbons is a necessary next step to getting us to a non-fossil fuel energy future, that it's a bridge to a renewable future, and that the reason it's a good bridge is because natural gas is cleaner than coal. So I want to address that in the next segment of my presentation to you. And this is all about the ultimate threat to human health, climate change. So you all know by now that the concentration of carbon dioxide in the Earth's atmosphere has been growing. It's been growing since the beginning of the Industrial Revolution. And this particular graph shows you the latest data acquired by the National Oceanic and Atmospheric Administration, which shows that we're now at about 400 parts per million of carbon dioxide in the Earth's atmosphere. And we're growing that concentration at about 1 million per year. Everybody knows this. Some people acknowledge it as really important and serious. Unfortunately, there are those in Congress, in state houses, and other areas of influence who think that this is irrelevant. But what not many people know, but you're going to find out tonight, is that carbon dioxide is not the only greenhouse gas of importance. And it's not the only greenhouse gas that has been growing. So the next slide also comes from NOAA, and it shows the concentration of methane. Methane is 1 atom of carbon, 4 atoms of hydrogen, CH4, the simplest possible hydrocarbon, also known as natural gas. And this shows the trend in the growth of the concentration of methane in the Earth's atmosphere, which, as you can see, is monotonically increasing, and certainly over the last 10 years has been increasing again after a hiatus. So why? Large-scale gas production from shale resources, and we are talking only about shale. The last remaining significant resource of oil and natural gas on the face of the earth is all locked up in shale. It's been saved to the last because it's the most difficult to get to, it's the most expensive to get to, and it brings problems that we never anticipated and were unprepared for. And those 3 problems are all related to climate. So when you burn methane, you produce carbon dioxide. When you burn coal, you produce carbon dioxide. When you burn petroleum, you produce carbon dioxide. The 3 sibling fossil fuels all produce carbon dioxide when they're burned, but at different rates. For the same amount of heat produced, you get much less carbon dioxide when you burn natural gas than if you burn coal or oil. And that leads some people to ignorantly think that because that is true, and it is, that carbon dioxide coming from methane is okay because there's less of it. That it makes methane a, quote, clean fossil fuel. No, it just makes it the least dirty because it still produces carbon dioxide. But as I just pointed out, methane itself is also leaking into the atmosphere. And it's leaking at an increasing rate. And it leaks either accidentally or purposefully from oil and gas operations. It leaks during the drilling process, and I'll actually show you some information that we just published literally 2 weeks ago on methane leakage from drilling. It leaks during the fracking process. It leaks continuously at the well sites, at the pad sites, from the wells that leak, and I'll show you some videos of leaking wells. It leaks during other processes, including gas processing and those processing units I showed you. And it also leaks from pipelines. The large diameter, high pressure pipelines, of which we have hundreds of thousands of miles in the U.S., taking gas from the Gulf of Mexico to Boston, from western Pennsylvania to New York City. But it also leaks from distribution pipelines, and those are the millions of miles of pipelines that underlay the streets of our cities. It also leaks from storage units, and it will leak from liquefied natural gas processing plants, which we're fast-tracking for construction in the U.S. The third strike against methane, from a climate change point of view, I already showed you when I showed you the picture of the, waiting for the bus to drive by here. I showed you the picture of the dirty flare. So when methane is incompletely combusted, you get soot, black carbon. And soot and black carbon also exacerbate climate change. So methane is a triple threat to climate change. And we're going to get into the details of each of those over the next few minutes. So I want to concentrate for the rest of my talk, almost the rest of the talk, on this issue of methane emissions. It's come to the fore. The White House produced a document a few weeks ago, a plan for reducing methane emissions from oil and gas operations in the United States. 3 years ago, nobody even knew about this problem except for a few people in academia and a few people at NOAA. No one was concerned about it, not at the state level, not at the federal level, and certainly not in the industry. And I was lucky enough to come into contact with a colleague of mine at Cornell University named Bob Howard and another colleague named Renee Santoro, and we set out in 2009 to start doing some research on this. Is it really better for climate than coal? 2011, that concluded no and no. We published that paper in a peer-reviewed, very prestigious journal, and were immediately chastised, pilloried, called every name in the book, hate email. We're told that we were lackeys for the coal industry, and we were absurd to even ask the question. Obviously, methane is a clean fossil fuel. And what we could to go out and actually do something that had never been done before. First question on slide 16. United States by oil and gas operations, either accidentally or by purposeful venting. No one had ever measured it. I repeat, no entity, no agency had ever done a systematic national scale measurement of how much methane is being emitted. And all we asked in that paper in 2011 was this. This is a policy issue that is so important. Rationally have come out of the same source, and yet they have. Draw your own conclusions. I have only 2 more slides, and then hopefully we'll have ample time for your questions and maybe even some of my answers. I'm going to show you the last 2 slides for dramatic impact, but they have very substantive content. The first is the one I'm showing you now on slide 36, which came out of a paper published 2 years ago in Science. And the paper was written by the very best and brightest climate scientists from around the world, a large number of them, led by Drew Shindell at NASA. And this was an attempt 2 years ago to forecast our climate future based on the best available information at the time. So the horizontal axis is year, starting in 1900 and going up to 2070. The vertical axis is global warming in degrees centigrade. The squiggly black line are actual measurements. Those are averages of the measurements made since 1900 up until 2010 of global warming. And you can see the 7/10 degrees centigrade warming that we've experienced in the last century. The 2 colored areas are a warning zone and a danger zone. The warning zone begins at a 1.5 degrees centigrade global warming. The danger zone at 2 degrees centigrade. Climate scientists largely agree that if we ever get to the 2 degrees centigrade, it's going to be extremely difficult, if not impossible, to reverse things. And if we get to 1.5 and we don't have already things in the works to slow down global warming, we could be on the fast track to the danger zone. There are 4 colored solid lines here, each of which is the result of computer simulation, forecasting, modeling, simulation based on the best available science in 2010, 2011, the best available computer programs, the most powerful computers in the world, and multiple models run at various labs around the countries, around the world, and then averaged. And each of those 4 colors corresponds to a potential scenario. What if? So the purple line, the uppermost one, is what if we do nothing? What if it's business as usual? What if it's all the above? We do nothing to substantially decrease the use of fossil fuels. Then the best available computer models say that we get into the danger zone, not in 100 years, not in 50 years, but in about 2035, 20 years from now, 2 decades. And we will get into the red zone in 2042, fewer than 3 decades from now. The red curve is another scenario that says, what if we were to have started in 2010 to substantially reduce carbon dioxide emissions? Well, unfortunately, that doesn't help very much. It only delays our getting into the red zone by 3 or 4 years, but we do get into the red zone. The blue curve is the scenario in which, starting in 2010, we have drastically reduced methane and black carbon emissions. And we can see that the climate quickly responds to that, and we delay getting into the yellow zone until 2041, and we wouldn't get into the red zone until about 2060. Obviously, the right thing to do, the right thing to have done, starting well before 2010, would be the light blue colored curve, which is to substantially reduce carbon dioxide, methane, and black carbon emissions. And had we done that in 2010, we would never get to the red zone. We would get to the yellow zone, but we'd give our kids and grandkids a much better chance than we're giving them. Of course, since 2010, 4 more years have gone by, and we're now here. And if we were to rerun these models, we would get different results because we're extrapolating to a shorter distance into the future. And those models are being run right now. And according to the IPCC, they're not likely to show a benefit of waiting, quite the contrary. So that's what the science forecasts for our future. And notice the significance of the year 2000. The last slide I'm going to show you comes from our United States Information Agency. It's a branch of our Department of Energy whose principal responsibility is to write the history of energy use in the United States and make projections of energy use in the United States. That's a good thing to do. Industry wants to have stability in its energy picture. We want to have stability for our energy picture. So what I'm showing you here is the latest history from EIA. That's everything to the left of 2011. And its projections, everything to the right of 2011. So everything to the left is history. It's what we did. In 2011, 26% of the energy we consumed in the U.S. came from natural gas, 8% from renewables, 8% from nuclear, 2%, 1% from liquid biofuels, 20% from coal, 36% from oil and other liquids. And what our government, our Department of Energy, our Obama administration is forecasting is that when we get to the year 2040, not much will have changed. I'm pausing for dramatic effect. Let me compare and contrast these 2 slides. If in 2040, what our Department of Energy forecasts will be the U.S. energy future, that's here. If that's true, then here's where we will be. And I can't accept that. And I hope that you can't accept that. These are forecasts. This is a scientific forecast. This is an economic, political forecast. We the people, control economics and politics. Science is controlled by natural law. We can't change the science, but we can change our political and economic future. We do that by voting. We do that with our own pocketbooks. So I want to conclude by thanking you for participating and attending tonight. I hope I've given you information that's useful to you. I hope at some point in the future I can come back and talk about those other two topics, leakage into drinking water from leaking wells, and what a sustainable energy future might look like. I hope I have that opportunity to come back and talk to you, but really looking forward to your questions tonight. Thank you for your attention.
Well, Dr. Ingrafia, thank you so much. That was a real tour de force, illuminating and also very sobering. I'd also like to thank you for your very generous offer to hang with us and give us a little bit more of your time for our question and answers. We did get started a little bit late, so we'll extend a few minutes longer. So for everybody on the call, here's what I'll ask you to do. On your screen, on the little tab that comes down from the GoToWebinar company, there's a little yellow hand. If you have a question, click on the hand, and then my colleague Julia will recognize you. She'll unmute you. Julia, maybe you could say the name of the person that you're unmuting, and they can go ahead and ask their question. And then after the question is asked, that person will be re-muted. So if you have any questions, now would be the time to find that little yellow, it's a yellow hand and a little white square, and just click on it, and we can see if we have any questions. While we're waiting for questions, I would just like to reflect on that very last statement that you made, Dr. Ingrafia, about we the people. I mean, I thought it was very interesting when you broke out your questions in terms of the technological question, the scientific question, and the policy question. But you're entirely right that it's the political and the economic where human beings have some chance of answering the questions that you've posed. And really important for us to take these issues into account as we vote, but also before we vote in talking to our politicians, in talking to our neighbors, and in talking to the news media and the other vehicles we have for public visibility that will get the message out that, as you were saying, this projected future is totally unacceptable. Julia, can you tell us if we have anybody who has submitted a question?
Okay, Laura Chamberlain, can you go ahead with your question?
Is Laura Chamberlain?
Yeah, I did not hear the question.
Okay, I think her question was, can you tell us how fracking for oil differs from fracking for gas?
Sure, thank you. Excellent question. First of all, as I said during my talk, it's important to understand that any new oil resource, like any new gas resource of any significance in the U.S. and abroad, will be coming from shale. So the question is, do you use the same processes and procedures to get oil out of shale as you use to get gas? And the answer is almost the same. You're still going to have multi-well clustered pads, so the spatial intensity has to be there because, again, the oil is distributed throughout the shale. So the companies are going to want to drill everywhere. They don't want to leave anything in the warehouse. You're still going to have wells that start out vertical and go down and turn and become lateral so that they go along and through along the shale rather than through the shale, or to rock layers just above the shale where the oil that was in the shale has migrated. The only significant difference during the well development process is the set of chemicals that is used for fracking. So in shale gas wells, more often than not, they use what's called slick water, which is basically water, 99% water, containing 1%, of course, of 10 million gallons, of certain chemicals that assist in stimulating the shale. In shale oil wells, more often than not, they do not use slick water, but they use gels, which are more typical fracking fluids that have been used historically. And that's because obviously oil is a liquid, natural gas is a gas, and it's easier for gas to flow through a low permeability source like a shale than an oil. Once the well is fracked, again, the only differences are that in a natural gas well, you have a different concoction of flowback fluid than you get from a shale oil well. And of course, at the surface, you have somewhat different results, because in a shale oil well, you're trying to produce oil. Right now, oil is much more worthwhile economically than natural gas. Natural gas is a throwaway product. In North Dakota, where we have the largest shale oil development in the U.S. right now, producing 1 million barrels a day, most of the gas is just flared. It's either flared or vented. There are no pipelines to take the gas to market. So the idea then is you can connect a pipeline directly to a oil well, or you can just show up with tankers, trucks. You can't truck natural gas away from a pad, but you can truck oil. You need a pipeline for gas. You do not need a pipeline for oil. As you probably read in the newspapers and on TV recently, you had a spate of accidents involving derailments of trains that were transporting oil in oil tanker cars. So the train itself becomes the pipeline. The processing, you don't need compressor stations for oil because you're not producing the gas usually. You're just venting it or flaring it. You're wasting it. You're burning it so that our kids never get to use it. You're lighting up the night of North Dakota and of the Texas-Mexico border. But you do need processing units. And one of the problems in North Dakota, I know this is a long answer to your very good question, but it's a very good question. One of the problems in North Dakota is they didn't have processing units of sufficient volume capacity. So they were putting not only the oil in those rail cars, but condensate, propane, butane, ethane, which is what made the transport of that mix of hydrocarbons by rail so dangerous, and it's still dangerous. Good question.
Julia, can you call on another questioner? And again, if we don't hear the question, if you could do as you did and repeat the question for us.
Okay, Ron Prosax, can you ask your question?
Well, I have another question other than the one I typed in, and my question is, what will be the role of natural gas liquids, especially here in Ohio? How is that going to affect what the industry does? Are we going to see a lot of plastic plants or new pipelines or what?
Excellent question. So natural gas liquids, also known as condensate, consist of the higher order alkyds. Methane is the simplest of those, and you go up the line: propane, butane, ethane, all the way up to benzene and above, and eventually you get all the way into petroleum. So right now, each of those is more valuable gallon per gallon, if you can compare a gallon to cubic feet. Obviously, natural gas is a gas, and these other things come out as liquids. They're more valuable because they can be used for chemical processes, plastic generation, propane, obviously, for home heating and for industrial heating, in lieu of oil or natural gas. So wherever you have wet gas, a wet gas is one that contains all of these gases and liquids together, you need processing plants. So one of the things you're seeing in Ohio that you don't see, for example, in northeastern Pennsylvania, where there's only dry gas, the natural gas that comes out of the ground in northeastern Pennsylvania is almost pure methane. What comes out of the wells in southwestern Pennsylvania and throughout eastern Ohio is wet gas, contains everything from methane all the way up to petroleum. So you must have processing units. And processing units are dirty. A lot of emissions, a lot of waste volume of liquids that are produced, a lot of burning, producing soot. And of course, industry, if they get access to these increased volumes of natural gas liquids, would be thinking about co-locating their industries in regions where they don't have to ship them very far. So the answer to your question is yes and yes. You will be seeing more processing plants being built. as long as the industry thinks it can continue to produce significant volumes of natural gas liquids in Ohio, and you're likely to see more heavy industrial activity moving into the area, especially plastics.
Okay. Barbara Warren wanted to ask if anyone is measuring the rate of growth of renewable energy in the USA.
Thank you for that question. Yes. So the Energy Information Agency, the same one that gave us the last graph that predicted our hydrocarbon future, also produces historical data and projections for all other sources of energy in the U.S. So a major source of information on past history and projected growth for solar and wind, geothermal, hydro, is going to the Energy Information Administration website. There are also industry-based websites. The American Wind Energy Association, AWEA, has a wonderful website that chronicles the growth of that industry. The solar, I forget what the name of the solar industry organization is, but you can Google it. So yeah, it's now easy to find not only information about the U.S., but information abroad about the growth of renewables. And don't let anybody tell you any differently. The growth is phenomenal. It's nearly exponential for those of you who are mathematicians. So hopefully I get a chance to come back and talk to you sometime about renewables and about how we've already developed preliminary plans for each of the 50 states in the United States. In fact, I would suggest that you go to a website called The Solutions Project, all one word, thesolutionsproject.org. And there you will find a map of the U.S. Click on your state, and you will get a very deep and detailed indication of what it would take to transform your state from predominantly fossil fuels to virtually no fossil fuels for any energy use by 2050.
Well, perhaps that's exactly the note that we want to end on tonight. Dr. Andrassia, thank you again, and this has been a wonderful presentation, and let me also say we would love to have you back and love to have you talk with us about renewable energy. We will have one more webinar in this series of 3. It will be a close-up look at what frackage has meant for the people of southwestern Pennsylvania. That webinar will be held in mid to late June. I think the date is the 17th, but I could be mistaken about that. But we'll confirm that, and then we'll be announcing it on behalf of Physicians for Social Responsibility. So if you're on our email list, you'll get that announcement, and if you're not on our email list, go to psr.org and sign up so you get it. Thank you all very much for being with us, and we'll look forward to speaking with you at the next webinar. Good night.
Good night, everyone.